This is also a special event within the ETF. We always have a special guest. And this year, Guido and I discussed quite a long time who should we invite. And it's always fun to invite somebody who is a well-known person within the audio world. And I think everybody can be certain that Tim is. He's been into valve amplifiers way before most people were. He's made a business out of it, and I'm sure he has a lot to tell us. Tim.
Thank you. Good. Good afternoon, ladies and gentlemen. I'm going to call the title of this discussion basically MyFi, not HiFi. And I'll describe that later on as we go through. Now I'm going to start basically with the most simple, boring subject, and that's called choke power supplies, or choke regulated power supplies if you like. The problem with CE certification now is harmonics on the mains, and most amplifiers still habitually use a rectifier circuit, and in the simplest form they'll have the capacitor, and we'll use silicon for the discussion. I'll draw it as a bridge rectifier. And we'll call that plus. And the most typical is a power transformer secondary with a bridge rectifier straight into and that's the usual boring circuit. And unfortunately, if you look at the ripple will have the instant charge with a slow decay, typical sawtooth. If you analyze the current by putting a current resistor, say 1 ohm here, and taking that off to a scope or a measuring device, you'll see that the current waveform on the sine wave is all at the tops and bottoms of the waveform, and there's nothing much, there's no conduction in the two periods between on the sine wave. So due to the losses in the transformer, the sine wave tends to get the tops and bottoms cut off. This, unfortunately, back to the AC, produces a lot of harmonics. The second problem, this is a peak rectifier, so if there is no losses in the transformer, your output would be the usual 1.4 volts times your input voltage. And a long time ago, and I did this commercially with transistor amplifier like the Musical Fidelity A470. I took the approach of, probably easier to turn over to get more space. If I draw down here, people won't see so easily. I will still use silicon because it doesn't matter, that vacuum tubes will still apply and have the same basic rules. And if I have an iron choke here, and if you get the design correct, we will know it as a swinging choke. And the problem is that the textbooks do not really give very good ways of mathematics. They give plenty of mathematics on trying to design a swinging choke. None of them actually provide a good design. The acid test of getting that swinging choke to be absolutely correct is if you monitor the current will have a pure sine wave on the current going into the bridge rectifier. If I monitor the input current to the choke, that will look like that. So in other words, it's the imaginary sine wave with a bit turned over. If you get it correct, you will see that you will have a conduction angle in those diodes through the whole 180 degrees. ultimately, of course, in every situation there are imperfections, so you might have a few degrees of glitching at the zero crossing, but for 98% of the time it is conducting correctly over the sine wave. So if you measure the current into the rectifier, it is a sine wave. Therefore, there are no harmonics back to the mains. You have now beautifully met to perfection the CE certification, because you've got no switching circuits that are going into the tens of kilohertz. So you have a very benign resistive load to the AC. Problem with designing a chip, the second point, if you get it correct, the voltage DC here will, if they're assuming no losses, correctly designed, will be 100% of the AC RMS voltage. So in practice, it will be in the order of between 90 and 95% of the voltage of the input AC from your transformer, assuming no losses in your transformer. Consequently, whatever distortion, if your mains coming in is a sine wave chopped badly like this, because there's a lot of thyristor lighting circuits or heavy industrial equipment in your area that distort and put 10% distortion onto the AC coming in, this will still hold, because this will tend to be the true RMS content of the power put in. So now you don't need all your line conditioners and other stuff to put in the way between your HiFi and your wall, because this takes care of it all. And therefore the logic is you have a filtered supply. Now the point, people don't know, the basic rule of thumb that I use is that the choke must be twice the size of the power transformer.
Physically.
Because the simple mathematics of the equation of doing this is that you now have a total DC content in this transformer. It will actually be 4 times the mass if you use the same core construction methods, whether it's if you can't do it with toroidals because there is no gap. And the simple routine is that if that is about twice the physical size of your power transformer, then with the DC content, that will automatically not quite saturate at the peak, but it will hold on and release its magnetic store of energy during the back part of the conduction, so that the diodes have an easy time. And so the simple rule of thumb is twice your power transformer physical size. And the average gap in a conventional EI arrangement is about 0.25 millimeter of paper is a reasonable optimum for the saturation. The only problem with this type of choke is noise. So you just have to have good vacuum bonding techniques and then pot it with a soft polyurethane resin into a box. Then you'll have a quiet choke. And to deal with small glitches, you can put a small RC network, which will typically be about 2 microfarad and 100 ohms, just to damp out and keep the tidiness of the glitches. And as I say, this now provides a power supply. The interesting point, instead of having a sawtooth waveform, the ripple here will typically be a reasonably clean sinusoid at 100, because it's full wave rectified, it will be 100 hertz on this point, 100 hertz rather than 50 hertz. But it will be nearly a sine wave. The second benefit, of course, for the same value of C, this sine wave will be in the order of 20 times lower, peak to peak, than the conventional sawtooth power supply. So your filtering is very simple. It's very benign. Typically, if you get this, because of this RMS conduction, there isn't any other reason but to be a bit of ripple, of a sinusoid due to the impedance of the capacitor. So it becomes very easy in a power amplifier supply where you're running 211 or 300B to have a second choke to the next capacitor, a second small that's not swinging. And that you can easily achieve 1 millivolt of ripple on that with values of capacitor only as low as 40 microfarad, 32 microfarads. You don't need 32,000 or these big monster capacitors to get a ripple down into the 1 millivolt region. And the only thing where you'll get, if the mains just moves up and down very gently, you'll get a small amount of undulation, but that's subsonic usually due to power line changes in your area, but it's usually very, very low frequency. And so this gives you a very quiet supply. It's bulky in that, or heavier because of the bulk of the choke, but you now meet the conditions of a very benign draw off the mains. The switch-on surge from the mains is very low. And the second point is that if you have a load and if it's designed correctly, and you know that you have a load of, say, 100 milliamps, and you can design this to work over a range of 100 milliamps to, say, 1 amp, a 10 to 1 ratio, with better than 5% regulation. Because that choke, as you draw more current, will saturate greater and greater. And therefore, the impedance from the rectifier will lower and you'll get a better charge. So this doesn't need complicated arrangements to provide very good regulation. The second benefit, of course, is on the diodes. Well, if we use vacuum tubes, I'm not going to draw a vacuum tube rectifier just to replace that, but we know that a vacuum tube rectifiers don't particularly like peak currents. And a lot of people try and put their GZ34 rectifier and have a couple of hundred microfarad capacitance on the output. When they switch on, it sparks away merrily. With a switch mode, or with a choke input filter, because you have an RMS, you haven't got a peak. The peak current ratio on here is in the order of 50 to 1 to 100 to 1, depending on the stiffness of your power transformer. That means that that rectifier, to try and provide, say, 100 milliamps, is having to charge with 2 or 3 amp peaks. Well, on a vacuum tube rectifier, the cathode doesn't like having to deliver that amount of current instantaneously. And the second problem is that the voltage drop across the diode increases enormously. And it will go up to about 80, 90 volts between the cathode and anode on a GZ34 on those peaks. So therefore, you never get the efficiency. If it's an RMS content into that rectifier, and the rectifier is conducting throughout the whole cycle, it now becomes an RMS value, which is what the book gives you as a typical constant value. If a GZ34 is 250 milliamps, you can draw 250 milliamps, and it will not complain, and it will last a long time, because there are no peak surges. When you switch the power on, switch your amplifier off and put it back on, the peak surge will not take out your hot rectifier. So the choke input filter, but not many people understand it in the modern terms, and a lot of the old amplifier, very few amplifiers used this except before the war, where capacitor values, high values, were difficult. But as I said, the whole point is it's a DC function in there. The behaviour of this choke in relative terms I'm going to come to. So as I said, with valve rectifiers, you'll then have a typical value on your GZ34 of, say, 40 volts loss across it. That's why I will derate that 100% to something in the order of just under 90% on a typical 400 volt supply. And therefore, I can take the output, because on now the behaviour of the choke, and this will lead me on to the second problem, that in amplifiers, we all like our single-ended amplifiers. Now, we have the usual triode and we'll have it self-biased for the argument's sake. And I will ignore the filament connections to the supply. And we have the transformer to the loudspeaker. If we take a 300B operating at 500 volts, which you can, I've done so, because it's a triode, if the optimum value of this transformer has to be 3 kilo ohms, for argument's sake, I don't have the values on the top of my head, and the output impedance of the 300B is 1,000 ohms from the anode, you have a damping factor of 3 to the loudspeaker. Now, secondly, because a triode has these characteristics which are effectively constant resistance curves, not constant current curves, ripple on the HT, if you have 1 millivolt of ripple divided by that tube, will end up at about the equivalent of 0.3 millivolt into the transformer, which is your noise output. So you have to have quiet power supplies to run a single-ended triode with no feedback. And my argument is if you, the step-down ratio of that, you might end up with the order of, call it 200 microvolts of noise, which is perfectly acceptable as far as I'm concerned. Anything below 1 millivolt of 50 hertz content or 100 hertz content is not normally audible on most sensitivity speakers. So that is one of the advantages of having a choke input filter that you can with 2 capacitors and 1 small subordinate choke to do the final tidy up of the ripple, get you down to a value with a nice clean sine wave through your tube to get an adequate signal to noise ratio. Now the problem, while I'm linking the choke with a single-ended, most people on most of the single-ended amplifiers I see have an output transformer that is usually pretty small, because Tango and these companies really don't know how to make a transformer that will satisfy my requirement of 20 hertz at full output. Because if you have an amplifier that doesn't get down to 20 hertz of full output, any subsonic information in the record will just modulate the audio that you hear when it comes out. And you'll have an amplifier that has a sort of an artificial warmth due to this modulation of the low frequency through the transformer. So at 20 hertz, let's take, we'll take we'll say we want 10 watts out of this amplifier, single-ended. This output transformer must, the simple ratio, the saves having to go through textbooks, is to call it a 4:1 ratio relative to a AC push-pull transformer. The mass, this is mass. Because basically speaking, when you double the size of a transformer in all dimensions, you have a quadrupling of the mass. Now, consequently, for a 10 watt amplifier, that output transformer should weigh in the order of 4 kilograms. A simple rule of thumb is 1 kilogram per watt on push-pull. So, single-ended should be 4 kilograms per watt, per 10 watts, the mass of the transformer. So you'll now see why a lot of the output transformers are just not adequate. If you design, because the single-ended is a magnetic storage device, which in a push-pull is not, you have 50% of that energy has to be stored in that transformer, because it has to give up that energy when the tube is switched off to provide the positive going waveform. So to get that energy, it needs the tube's input plus the 50% makes it 100%. So to give up that 100% is a 200% voltage, consequently the 4:1 mass ratio. And so if you have an output transformer and you, with back to the EI, very simple shortcuts with the eye. Typical value of gap is going to be 0.1 millimeter of paper. That is a reasonable optimum to start with whenever you're designing an output transformer for single-ended. So the simple answer is, instead of having to calculate a single-ended from scratch the hard way, design as the AC. If this is 500 and the tube can only switch, you've got approximately 600 volts peak to peak or 200 volts RMS on the primary. You will design that as if it was a transformer for, in push-pull terms, you'll treat that as a 400 volt RMS transformer. If you put the gap in, then that transformer, this ratio is for 20 hertz, will give you a transformer that can give you good bass handling, which most of them don't, and therefore give you a cleaner, slightly leaner bass. It's not quite so romantic, so it's not quite MyFi, it's more HiFi. Now, the other shortcut in transformer design, but I don't know if I can do it this way. Save on paper. On a push-pull transformer, we have an EI. A toroidal, the calculations are very similar, but let's draw that. We'll neglect the I section for the drawing. The convention is that you calculate cross-sectional area of this area. So a typical transformer may be 32 millimeter, this dimension, 32 millimeter. And if you have a square stack on a bobbin that is 32 millimeter, that is going to, I haven't got the calculator in front of me, to give me the square centimeters.
Approximately 10.
It's about 10.
Pardon?
10.
About 10 square centimeter. Okay, well, the simple rule of thumb, instead of doing the calculation of flux and BH and the curves and everything to do, everybody then routinely, boringly does all the calculations from square one. Well, 40 years ago, when I was manufacturing transformers in South Africa, I took a shortcut, formed a set of tables. So instead of having to do the calculations all the time, just look up the tables for that particular core size, boom, plug numbers in. Simple rule of thumb, on M6 core, with about 12,500 Gauss, or 1.25 Teslas, flux, which is a reasonable, non-lossy, not pushing it to the saturation. The rule of thumb, 1 centimeter squared will, on 50 hertz, equal 40 turns per volt. So 10 square centimeters means that's going to be 4 turns per volt for that transformer. So it's a very simple rule of thumb. Don't have to waste time. That's for 50 hertz. Right, for 20 hertz, that rule of thumb, conversely, is going to be 100 turns per volt. So that's going to be 10 turns per volt for 20 hertz on that. This is a push-pull transformer with no DC flux, no standing current in the core. The same rule applies for a power transformer. You know, if you're designing a mains transformer and you know that you will need on 50 hertz to work on the percentage of 40 turns per volt per square centimeter, or in inches 6.3, 6.4 turns per volt per square inch. The two simple numbers, even to work for that flux density or thereabouts. So why go through the aggro of having to calculate it all from square one? Right, for a single-ended amplifier, we now have to take that factor and multiply that by 4. So we now need 40 turns per volt on that core size. So it's quite easy to see that on a single-ended transformer where you have to go to get a transformer that will get to 20 hertz without. The acid test is that you get your sine wave on a single-ended at 1 kilohertz. Well, at 20 hertz, if you can tolerate that amount of a blemish of saturation of the energy not quite being able to sustain to hold it all the way through the full cycle. The downside, the tube will take care of it and give you a nice clean. The top side, you'll have a little bit of tear. But a lot of single-ended amps, when you try to drive them to clip, they are doing this sort of waveform. And that is manifestly audible when I listen to these amplifiers driven hard. They start crumbling and grunging because they can't hold up on the bottom end. And that's modulating because you've now, once it's saturated, you've now deprived it of transmitting the mid-band frequencies through. And if you do an IM distortion measurement, you'll correlate this. So that's a simple rule of thumb. These sets of numbers gives you, so a single-ended amplifier, the output transformer will, in round figures, be 4 times as heavy as a push-pull amplifier. So it's a very inefficient device. And as I say, Tango, and all these companies, Hammond, all their single-endeds are woefully inadequate to meet my criteria. The nearest, perhaps, is one of the Tamura series. They get fairly close. They do a 211 output transformer that's supposedly for 25 watts that weighs 10 kilograms. It's getting close to what you want for a transformer. It's about the best that you can buy out there.
Bertolucci has a 14 kilogram.
Sorry?
Bertolucci has a 14 kilogram model.
Who?
Bertolucci.
Bethology.
No, Italian. Bertolucci. Bertolucci.
Bethology.
They have a 14 kilogram.
Yeah, but now, if it's packaged in a package like Tamura, take away about 2 kilograms of all the potting stuff.
Okay.
And these James transformers or something coming from Korea, take all the gubbins away and you've really got a fairly naked little rat inside. You know, it's packaging to look good. Very old trick. I mean, Lux, we did the same thing. And as I said, this is the criteria, that the naked transformer should weigh in that order. Now, I personally don't believe in toroidals because you can't make a gap to control. The secondary formula, another cheap trick is if I extend the stack of that core by twice as much, in other words, I now make that transformer stack 64 millimeters. I've doubled the power rating of that transformer, but I've now only increased that amount of extra copper wire because this part, the turn of the wire going this direction and this direction is a constant. So I've now only increased the wire length by less than 50% for that doubling of core stack. So why my transformers are all high, deep core stacks. The second point, well, the other point is, and I have done a transformer ridiculously to the extreme, that is a stack that long, and you're winding a bobbin that is very long. The performance is wonderful. It's just not commercially viable for me to do it that way. But the other thing is trying to get bandwidth through an output transformer in an amplifier. And the point is that with a large core, the doubling, I now can reduce those turns by half. The number of turns to wind a primary, now the self-inductance of that winding has reduced by a quarter. Because I've got thinner or thicker wire and less turns, my capacitances between all the layers are reduced. So I can now extend the high frequencies by interleaving methods right out to 100 kilohertz quite easily. So what because the secret I want is the minimum amount of copper and the maximum amount of iron. With a toroidal being a donut-shaped object, the cross-sectional area is actually quite small. So toroidals end up with a high number of turns to achieve the same power transmission. Because they have a high volume of turns, the self-capacitances become ugly. And it's harder to design a toroidal with the same bandwidth parameters.
What about C-cores?
A C-core, well, if you take a simple single C-core, I'm not going to draw the other loop. If it's only a little tiny square, it's a very small back to a toroidal problem. But if you do a C-core that is like this, about that long,
I mean, deep.
very deep,
Yeah.
which you can do it, then you have got a lot of cross-sectional area relative to the turn loop. Now you can keep the copper down. Yes, but nobody makes a C-core to that profile. You can glue a few side by side and make your own. Problem with C-cores, you've now got to make bobbins to go on them. And the best method, you can design out transformers where with the two C-cores you have a bobbin on this side and another bobbin on that leg. You've got to make two very small bobbins. If you make it this deep, you now have a bobbin hole where you have to make a mandrel on the winding machine. So the wire is going on and you're trying to make it lay flat, go around the corner, lay flat, go around the corner. So there is this inevitable problem when you go to a very deep stack. But if you can manage it and you're painstakingly careful, you can wind a very good transformer. But a C-core has no advantage over an EI, because the standard C-core has the standard 0.3 mil thickness of lamination, the standard, and you are relying on a ground gap to make it work. EI is intrinsically lapping the gaps. In push-pull operation or in single-ended, you can gap it controllably. A C-core is much harder. There is no magic about a C-core. C-core became a fashion in the 60s in England. I've been through there. I've used a couple of C-cores. I just gave them up as a bad job. They delaminate. You pot them, the epoxies, the thermal characteristics, the heating and cooling, their gaps start opening up and they get noisy. AEIs are much easier to control. It's old-fashioned, but what's wrong with that? So what I'm trying to say is a C-core and a toroidal has the same problem. Now the second problem with trying to wind an output transformer, you try to wind on the bobbin, you want to wind your turns accurately side by side for your speaker wires. Typically, it will take for an 8 ohm, for 16 ohm, I'll come on to why on the net Hammond got it wrong and people didn't understand the question I kept throwing at them. Why couldn't they get the same? They kept saying that the response on 16 ohms was like that, on 4 ohms was something like that, and on 8 ohms it was something like that. If you're winding your secondary immaculately tidally, you want to occupy a complete full layer, because you have the primary with its small wires here with a magnetic sheet conducting into the secondary. Well, if the secondary only went this far back, the magnetic sheet into this pair and this makes this react to that part and you get a loss of performance. And the secret of any output transformer is how I look at other people, how they're winding their secondaries. The primaries, because they are variably hundreds of turns, will tend to occupy near enough perfect layers. And the small sheet of current for the last tiny bit, if it folds back, is so minuscule relative to the whole bulk. Because a transformer, you have a sheet film that is roughly it has a thickness, the coupling for leakage inductance is proportional to the thickness of the stack of the winding. So traditionally I'll wind 1, 2, maybe 5, 6 different layers for the secondary. Now the Hammond, nobody ever thought about this. The 4 ohm happens to be there and this end. The 16 ohms here. Where's the 8 ohm tap going to be?
Halfway.
That's 8 ohm here. What did I say? What did I say about this point? Why did nobody understood and answered my question, and I kept throwing it back endlessly until I got sick and tired of being shouted down. Why Hammond didn't understand that trick. They had designed a transformer with an incomplete layer on the 8 ohm tap. There's 2 ways they could have done it. They could have had the 4 ohm and the beginning of the 8 ohm winding split. So you had, this is your 4 ohm, and then you start again with this is the beginning of your 8 ohm, split that winding, take it to the end and join it to the end of the 16, and take the beginning of that and join it back to this naught and call that 8 ohms, and sacrifice the 16 by just jumping externally. Suddenly that transformer will now have the same bandwidth. Nobody ever figured that stupid point out. And so I'm just trying to say, Hammond...
Partridge did that. Partridge did that. Partridge did that.
Partridge, of course, understood this. But I'm just trying to say Hammond didn't, and the people who are asking didn't understand it. So you now know it in hindsight that Partridge did it. Partridge understood this. That's why Partridge transformers are good. I'm just saying, why didn't Hammond figure this one out? And you guys, or all the people on the networks, on the do-it-yourselfs and the audio silence, never understood why they had this problem. So they didn't see the wood for the trees. There are all these audiophiles that will mathematically shoot me down, but they can't see the wood for the trees.
Yeah.
And that was the point about the Hammond, that it was poor winding. And they should have spotted that. And a lot of these transformer companies in America have all just picked up drawings because they didn't have, nobody has any prior knowledge. The textbooks don't discuss this problem properly. Langsford Smith is about the best of the books for describing transformer design. And it still doesn't quite define this trick. Now, at Lux, we use different methods where we could have all 3 taps available. By each set of windings, we would rearrange the beginnings and ends of those starts all the way through till we had an even field coupling on all the total couple, because we paralleled up all the layers by using thinner gauges, and we made sure that each tap occupied a complete layer. That was all the Lux transformers, and I did the same when I designed the output transformer for the 3045. But on the 3045, there was another cheat. Instead of doing that, I wind with a double section bobbin. So I put some of the turns on this side, some of the turns on this side, and I have some of the primary on this side, some of the primary on this side. Then I always managed to get a good field coupling. And that's why the Partridges were double section bobbins as well back in the 50s with the Williamson transformers, because that's the trick that they saw. It had the other advantage, of course, your capacitance factor was much lower. But that is the main point. Right, I'm going to leave the subject of that and come to tube, back to right, I'm going to just, in a nutshell, take and call that loudspeaker output. This is the Lux M3045 amplifier designed back in the 74. Everybody knew that I had triad strap tubes as the output. Now the point was, if I go to this type of transformer configuration, one of the problems, everybody just does their usual output. Plates, HT, and a trouble with a valve, it can pull on, but it can't push off. So you have to rely on very tight coupling between the two halves of an output transformer to get high frequency performance. And nearly all the classic tube amps at 20 kilohertz start wilting and giving triangular shaped waveforms as they try to clip. Now, Macintosh saw the trick, but Quad didn't do it the same way. Now we'll take that center tap down to ground. On the original starting of the design, I wound my output transformer this configuration. Firstly, because I've now got the total terms split down by a half, my inductances here is now a quarter of what they would be on a conventional circuit. So I have less capacitance effect from the windings affecting the top-end bandwidth. Right, I'd cross-couple the anodes this way because I always treat plus grid plus cathode as my phase sense of the amplifier. I treat it as a cathode follower. Second problem with that, conventional, we were talking yesterday about pentodes and ultralinear and triodes, and trying to get this impedance down into the transformer. An output transformer, assuming no wire losses, if fed from zero source impedance, will have zero distortion. End of story. So, intrinsically, a cathode follower has a cathode impedance based on the mu GM factor. It's in the order of about 10% of its anode resistance, typically. So, on a KT88, if it's 4 kilo ohms, we've got about 400 ohms of cathode impedance. So we now have a low impedance drive into the transformer. So the base response of the transformer improves enormously because we've now got a low impedance source. And yes, you need a higher voltage to drive this, but that's not difficult. Not difficult to get a high voltage. But if we have on this amplifier, and I had 450 volt power supply for the KT88s. Typically, if the tubes could switch to zero on perfectly, that's a 900 volt peak-to-peak swing on the plate. Well, now it's half that. So I now have 450 volt peak-to-peak on the cathode, which in round figures is 150 volts of RMS of grid drive. 150 volts is not difficult to get hold of from a driver tube. On the Lux, because they wanted to try, the fashion was in Japan was Triad, I decided to do something a bit different in the prototype to demonstrate a point to the company, and it was then exhaustively listened to in the listening room at Lux for about 2 months, 3 months before the go-ahead, and we turned it into a production reality. I used, and this will be the secret, how to fix all your MB3045s. My original design was KT88s, because there was no other tubes I could conveniently find in Japan that would do the job I wanted as a target design. I wanted a target performance of about 70 watts output. Right, so I wound the output transformer for this into, and I'm ignoring the speaker taps for the moment. The second important feature of this output configuration, which I applied and took patents in Japan, I have 2 capacitors coupling this anode, which is the same side windings of the transformer. This transformer is bifilar, but it's not an infinitely tight bifilar winding. So it's not as if there is zero impedance between the 2 terminals on the same side of the bifilar winding. This capacitor now makes damn sure that the 2 starts of that bifilar are rigidly coupled. The same with this end. The value of the capacitors doesn't matter. It could be 2 microfarad, 1 microfarad, 4 microfarad. Now I've got a very low, tight coupling from this cathode to this start winding, which is the anode of the opposite tube. Right, well, as I'm driving this tube, as I turn it on, that capacitor helps to jack that other tube off. So now I don't have a high frequency limitation problem. Now it's easy for me to get 100 kilohertz full power, like that. I don't have a slew rate problem because you now have true push-pull because you can pull and that's let off. So this circuit I call balanced bridge.
TG.
Yes, sorry. Trying to read it from there. I call it a balanced bridge configuration because if I reinterpret that, what have you got in a transistor amplifier? A pair of transistors with a split supply with a loudspeaker connected. So you have two supplies. That is this element here, that is this element here, coupled by the capacitors to configure that effect. So I call it a balanced bridge. And then all these old-fashioned conventional output configurations just becoming awfully slow and boring. Back to MyFi. It's MyFi of sound, not HiFi of sound. Right, well when I did the start of the development, one further trick I could do with this. If I take this grid 2 and couple it to there, I have Triad Operation. I did this with a switched circuit. I had made a switch with 3 positions from that grid. I'll take the I'll take this position as the triode and ignore that. If I then take this to the opposite, yes, to the opposite anode, I have pentode. So this is T for triode, P for pentode. But one other trick I did was to take that other position up to the HT, and that I call ultralinear 50% tap. Because an ultralinear is where the screen grid is a percentage of its output. Well, if I take that screen grid and hold it at B+, as the anode is going down, so the cathode is coming up. So that screen is seeing 50% relative to its cathode of the voltage. So it becomes true ultralinear with 50% tap, not 43%. It might be a small difference in distortion between 50% and 43%. Right, I then built this amplifier with this switch so I could demonstrate triode, pentode, ultralinear. To get the output in the triode mode without drawing, you couldn't achieve 70 watts without drawing some grid current. So I had a voltage cathode follower coupled to this grid, and it was that funny looking tube, the 6045 tube that everybody can't get hold of and wondered what it is on the MB3045, about the size of a 12BH7. Well, in fact, it was a 6FQ7 that I had NEC select for a high voltage rating without leakage currents. And we made them house number it to our number. So that's the history of that tube. It's a selected 6FQ7 because I'll explain. To drive this high voltage, now I simply take this anode to here so that the anode to cathode through the swing is constant. Only the error of driving the grid relative to the cathode appears on that tube. So it behaves like as if it was a conventional push-pull output with your grounded cathodes on your power tubes driven by a cathode follower. I did this so that I could guarantee the same performance in triode mode as I could in ultralinear or pentode. In the listening, I had the switch set up and let people play. Nobody could really, honestly, without looking at the switch, ascertain whether it was a triode output, pentode output, or ultralinear. There was no sonic obvious difference between any of the nodes. This was my method to disprove in 1974 to the people that there isn't a thing as a triode sound or a pentode sound or an ultralinear sound. There is how the whole architecture of the whole product is that modifies that sound of the product.
Is there any difference in the distortion measurements?
There was differences in the distortion measurement, small differences, that's obvious.
What about the amount of power?
The amount of power, I did it so that I would guarantee it would, in triad mode, be about 70 watts, which it was in production a 70 watt amplifier. In pentode it gave me 80 watts. Half a dB, quarter of a dB, nobody can hear that, unless even when you boot the hell out of it. So it's semantics to try and hear that difference in power. Yes, on paper there's a greater power in pentode. If I had productionized this as a pentode, I wouldn't have bothered with the cathode follower. I could have saved a tube in that product. But the company and the Japanese psyche is triodes. So I said, well, this was my way of getting at them. I've made this amplifier with 3 modes. And then at Lux, they would sort of, yeah, I can hear a difference. So what I did next is, on the rotary switch, I'd move the wafer back off the mechanism and let them play, thinking that they're changing. And nobody spotted it. So my whole point was, because I'd intelligently worked out what to drive this transformer configuration, it didn't matter what I did with the... But for production, I left it as triode. So I then went to NEC, I looked at all the parts that we could make a tube with. And I found enough parts to make what is effectively a KT88 size package. I wanted 45 watts. There was a tube. I got them to weld some plates onto the anodes to increase the surface area and increase the dissipation to get 45 watts. I got them to put a nice little silver skirt on, just like a 6550 or KT88, make it look pretty. And we called it, I've forgotten the part number for that tube now. But I said, right, well, it's got to be internally wired so they can't break it apart. I'm catching them all out on this triode penta. It's now going to be fixed as a triode. So I get the tube made where internally the beam plate, it comes out on the same pin, pin 4, but internally it's wired back to the cathode. To pin 3 on the anode. So we have a triode de facto, a new number on it. And the point was, at the time, it also gave me a degree of exclusivity on the product, or gave the company, because when people want to service it in the field, they have to come back to buy the tubes from Lux. And
so it was actually a beam triode.
You could call it a beam triode if you like, but it is nevertheless a triode, as all those 50C10s and all the other triodes, they're all basically beam tubes wired up, rather than pentodes. I should call it a beam function, but a suppressor grid. I mean, the beam plates was RCA's way of getting around the Phillips patent of the suppressor grid. And it's just a different method of arranging the way the electrons bombard the plate. But that was the whole trick, and the cathode follower, which is basically a 6FQ7, was designed to give this. The second point with this balanced configuration, I can take feedback from the cathodes, and take that back to my tubes. I haven't got any feedback around the transformer. Therefore, the amplifier has very good stability. For commercial, to give it that classic, what I call warmth tube sound, back to MyFi, not HiFi, I take about 6 dBs worth of feedback from the speaker terminals back to the main feedback point, because I want a bit of that phase shift quality to give the warmth of sound. And that is how that product became into being. So I designed the output transformers, the chokes, the power supply, the whole shooting match of that product.
Any idea what numbers they were produced, these amps?
Lux would not make an amp unless the production run was in the order of minimum 5,000. Now, the mains transformer I designed, as all products there, you would design a mains transformer for 100 volt primary only for the domestic market, and a mains transformer for 120 volt for the US market, and for Europe, a 220, 240 volt primary. So, therefore, people buying amps from America would be stuck with a 120. There wasn't any way of reconfiguring. But that was economic because they were wound in-house, and it was simple to wind one primary, save all the time of splitting it up and putting junctions on it. And the second thing was unique about the product, I made it as a mono. At the time, in '74, there were no mono amplifiers on the market. Everybody had gone fully to stereo, or quadraphonic. Because quadraphonic was a big fashion between 1970 and '77. And I put it to the company that we wanted to make an amplifier that I think that would do well in the American market. The target was for America, where the higher power. For Europe was still satisfied with little 10-watt amplifiers. Anyway, I put it to the company, let's do this mono amplifier. Because if people want quadraphonic, they buy 4 of them. If they want stereo, they buy 2 of them. And that was how I came up with the monoblock. And I even spelled it M-B-L-O-K. And people have copied that spelling. So that is the basis of that. I'm not going to draw the rest of the circuit out, or the power supply, but suffice to say that for the bias, for the cathode follower drive, we had a negative supply of about 200 volts. I even had the capacitor manufacturer make us some special capacitors with a common positive to save by having 2 capacitors or 3 capacitors in one brick with a common positive and 3 common negatives, so they had to isolate them internally. And so that made it difficult for people to repair if that went wrong. And that was, it's one of those things that the psyche is there. You don't want people to possess the product beyond 5 years. In Japan, the life cycle is 4 years, and because the reason is Japan is taxed on the stock of spare parts. Every year, when the accountants check on the spare parts, that is taxed at a high rate. So at Lux, every year, anything that was deemed over 4 years old, knobs, chassis, bits and pieces, came out and were thrown into a bonfire. They were not allowed to crush them, they were in a bonfire. And so amplifiers, tuners, all sorts of bits and pieces just ended up in this big bonfire in one of the yards every year to burn. Didn't matter what. So if anybody had a product, and this went for the motor industry, if you had a Toyota, if you had a 4, 5, 6-year-old Toyota, tough, you can't get parts. That's why in Japan people do not keep cars beyond 6 years, because you can't get parts easily. In the West, there are people that make copy parts, but that's the same with electronics. So, as I say, that the intended lifespan was about 4 years. It ran just over 4 years. And that's how that came into being to go to America. And this was my little joke on people about the output configurations. I said there isn't a sound. It's the configuration, how the whole thing is put together as a total entity, the architecture that characterizes the quality. Now, I'm not going to describe another Lux product because it's not part of what I wanted to talk about. Now, we were back to the single-ended transformer, and we were arguing about, there was a fashion for this method. I'm ignoring bias for the arguments, what people call the parallel output.
Oh, parafeed.
Parafeed. The reason this became into being is if you go back to the 1930s, so you have to understand the concept of the mindset of the people in that era. Everybody now has jumped on it as a bandwagon, as a fashion, but they really don't understand. They think it's some magical, it must be better. The reason it was done in the 1930s was new metal was just beginning to come into existence, but the silicon or the steels for transformers were relatively poor. They hadn't got grain orient silicon yet, and so trying to the roll, just the conventional pressed steel plate chopped up into laminations was, with a high carbon content, was fairly crude. So it saturated about 10 kilogauss, 1 Tesla or so. Right. Trying to get bass response out of a simple, if this was an imaginary output transformer with a speaker here, trying to get bass response meant you would have to wind a ridiculous number of turns on the core to try and get the bass response. And by the time you've wound that many turns on it, you have no high frequency left. So this transformer now becomes bandwidth of 50 hertz to 300 hertz, 500 hertz. That's not audio. So the solution was, if you wind that as purely a choke rather than a interlaced, you can now control the capacitance on that winding for the same given turn. And a lot of these had as many as 15,000 turns. And a lot of them would, on the paper chokes, would do a double section bobbin and pi wind it to get the capacitance down. But on this type of transformer, you couldn't interleave it and do it successfully. So it was easier for them to wind a choke that met the criteria. It's still got the same iron, so it's still got the same base deficiencies if you lower the amplitude to a very low level. Then they used a capacitor to couple it into what would be a transformer that used nickel. At that time, they only had, in those days, what we would call now radio metal or grade B silicon, which is roughly a mu of 20,000, 30,000, rather than the mu of 250, 300,000 for pure permalloy. But you could now wind a transformer with relatively few turns to transmit that power. So that's why this came into being back in the 30s. It was when Sauter had discovered mu metal properties back in the late 20s. It became into being, and the Western electrics went this route. The Japanese all look at this and, wow, there must be something better, it must sound better. And the other thing I saw on the internet was the point about having this capacitor coupled, if this was bias, to the cathode. Well, if you look at the 1930s, trying to make a capacitor that went from here to here that was, say, 100 microfarad and 25 volt was, in those days, incredibly difficult. In the 1930s, low voltage electrolytics didn't exist. Well, the only other solution to get the same parameter of stiffening up the cathode impedance was to put a capacitor between the HT and the cathode and make that 4 microfarad or so and a high voltage. So that's why that came into being. And now everybody's saying, well, this current loop is better for it. And that's really not quite the truth of it all. It's just, but it just conveniently fits the model that people can discuss about in the webs on this, so that this grid is now supposedly not inside the circuit. But that and that both constitute the same method because of, as far as the operation is concerned, it was just that the task of doing it was easier lower. So that's the history of why the Western Electric went to this route in the 30s, this type of route. Now, a lot of the amplifiers they were making were only in the order of anywhere between 1 watt for a studio line amplifier to drive a transmission line to some other equipment in another studio, up to maybe 20 watts for cinema use. Powers of amplifiers were very low in the 30s. I've forgotten to bring my book up showing prices from Mollard in the 1934. A typical tube was at that time 3 or 4 euros for a small 2-volt battery tube. Mollard did a DO60, 60 watt anode dissipation triode. That was £8 then. Well, that was a month, more than a month's salary. Price of tubes was very high relative to the price of iron, loudspeakers, or any other fabrication process. So the companies like the Western Electric had to maximise every ounce they could get out of a tube in performance because of the price of tubes, especially in Europe. And so that's why a lot of the designs we see evolved where they would use transformer coupling because they could get more efficiency by having a step-up ratio and get a little bit of free gain that way. So this is the heritage of where we're coming from. And to say now this must be better isn't necessarily so. You have to think of the mind of how people had to develop. Nowadays you can buy 1 million transistors for the price of one of those tubes. And so it's just an argument that I said, right, this is how that came into being. If you want to do a singlet, today with silicon, there is a crossover point between where this method has to be used. And this is used commonly in studio equipment like the V72 microphone amplifier. That uses this type of method. And the Germans in the TAB back in the early 50s, when they designed the V72, had the ability to design a choke. They had a plastic bobbin with 4 partitions. So they could pi wind 4 pies in there and get incredibly low self-capacitance. So they could now make a choke with 200 henries, 500 henries of inductance in a small package this size, simply because they had the ability to mould a very beautiful bobbin and pi wind it so the stray capacitance is incredibly low. Therefore, the self-resonance with this tube is going to be in the 50K or beyond. They had then got proper mu metals, so they could now use a relative mu metal transformer capacitively coupled to drive your transmission line. The reason that you can't use mu metal in an output transformer, and I'll come back to come to this, is, and I'll come to the crossover equation, basically the rule of thumb on where that method doesn't apply, and that's why on conventional single-ended I choose to use a single output transformer. On a tape recorder, have let's do it this way, a playback head, and the head has windings here, like a cartridge, off to a tape Repro amplifier. And a Repro amplifier is something like an R8. It's similar to RAA in its function. It's not exactly the same curve, but it has similar, where it needs a lot of gain at low frequencies. Now, this core on a tape head is usually pure, what I call 78% nickel permalloy. Now, the mu of permalloy on a curve, something like that. Yes, they're discussing about nickel, steel, other steels where the inductance or the mu fell back to some very low value at the beginning. To prove that mu metal has a value extending almost all the way perfectly back to the 0, and it's typically 200, call it 300,000 mu. On a tape playback head, and to show that this is true about dynamic range, on my 1-inch tape recorder, which is 12 millimeters of mu metal per channel, per track, I have a resolution of over 80 dBs of dynamic range. If the tape passing here has, for 0 dB output, equals 200 nanowebers per meter, it's not very much flux. It's quite modest flux that's on that head. Now I go to minus 80 dB, you'll start to see the value of the flux is sub-nanowebers, sub-femtowebers. And that head has got to reproduce the low frequencies. The quality of the low frequency reproduction has to be the same when it's up in this region. 200 on mu metal, that is roughly 5.5 Gauss or 5 kilogauss before it starts to saturate hard at about 6-7 kilogauss, depending on the rolling process. Well, if I go all the way down 200 nanowebers, I'm starting only with that as a maximum level. And I'm operating way down into the microscopic levels with that tape. So I can prove that the base response I measure at minus 60 dB is the same as I do at 0 dB. Therefore, mu metal consequently has to go all the way back. The standard sheets drop it off just before the bottom. They never draw it dropping back to the origin. It does definitely come back. So it's near enough a flat line all the way back to 0. So there isn't any problem with switching domains. The mu metal, the BH curve has to, because if I'm playing a tape that is recorded linearly, if there was any BH, if there was any of this problem on the playback head, then you would have a very distorted sine wave. And therefore, mu metal has effectively are very, very linear, no hysteresis. And that is the proof of there's no hysteresis on a tape recorder. A typical quarter-inch machine or a cassette machine, you've only got 50 dBs of dynamic range, so it's a bit hard to spot them, to find at them submicronic. But when you've got a large format where the noise figure becomes relatively small, I can extend this all the way down. The only reason tape recorders cannot go, I can at 15, the reason I can't go much below 7 hertz, as you've got a tape that's, say, 38 centimeters, well, per second, if you're 10 hertz means that's 3.8 centimeters, the wavelength of the flux on the tape. Well, that wavelength going across the head, some of that will be a positive domain, some of it here will be a negative. Some of it then couples by the back, not through the gap, and cancels. So that's why the typical tape recorder bass response falls fast, because you have a wavelength on here where part of it is cancelling on the back part of the coil, and you can't shield it to avoid it. Because at the mid bands, all the energy is a flux across that gap, and you're trying to differentiate. And if you imagine the tape this way, high frequency, the bars are like that. So it's very easy as you move the head to differentiate these flux changes and get a lot of output. As you get to a very long wavelength, the head has a very small, the slope then of that differentiation becomes like that instead of this type of a slope. So you're trying to differentiate tiny amounts. So that's why the bass ultimately falls, because of total loop length. And the only way you can extend that is to make this head that much bigger to get better bass. And so that's what I try to do, is design head or get heads made to my design which are large enough to improve the bass end response. And a lot of the cassette machines have a tiny little head that's so tiny. A lot of early Nakamichis at 30 hertz dropped off like a rock, the very early ones, with this sort of an effect. And they eventually made big, slightly better heads for playback. But a record head can be as small as you like, because you're recording and leaving a flux at the gap with the bias. So the magnetic properties doesn't matter, because you're actually leaving the tape on the energy on the tape. So that is my argument about what Permalloy's capabilities are. The proof, what I call the proof of the pudding, that the permeability behaves. So my argument is I use this in cartridge transformers, and I have no problems with loss of bass at any level on a cartridge transformer, down to femtovolts, let alone microvolts. You will not be able to reliably measure any problems in a new metal core. That's why they're ubiquitously used in microphone amplifier and microphone transformers for microphones in the broadcast industry, because the cumulative error, if you go through 10, 20 stages, you're going to compound the errors. Because every time you take a dB off, and the next stage takes another dB off, you end up with successive. Well, in broadcast industry, new metal has stood the test of time. So there isn't a problem. And that's the first simple answer to it. And I then, despite the argument yesterday, I then did a point with a single-ended output. A configuration I use in a line amplifier of mine. I have a single-ended output transformer, and I did this design about 13, 14 years ago, which is used in a couple of my preamps, and is also used in some of my broadcast studio equipment. Instead of using the parallel feed method, I spent a lot of time trying to design a single-ended transformer on this is a ECC 82 drive tube, or the original design was a PCC 88, and the PCC 88 I operate at plus 160 volts, because I can then get quite a lot of current and quite a lot of power out of that PCC 88 without jeopardizing its life. If on a single ended, that voltage will double to about 320 on the off cycle, and ECC 88s do not like very high voltages. The trick was to design that output transformer. So I have a lot of turns and I used M6 lamination. It is the methodology of how I interleave those laminations to what inductance I achieve. In open loop with no feedback, if I measure a base response at 30 Hertz minus a dB, say at an output here of 10 volts, and I do the step and go down successively in levels, the high frequency won't change, sorry. The low frequency will change slightly. By the time I'm to minus the output, that's 10 volts is approximately plus 22 dB relative to studio practice. If I go to minus 60 dB, which is almost nothing audio that you can hear, then the bass response now has this. It's about an extra 10 dB down at 30 Hertz. But the Fletcher-Munson curves we were talking about yesterday, our hearing isn't much good in that bottom end, so it doesn't matter. You can't hear that there isn't any, the bass is slightly less deficient at minus 60. You're talking about audio, about the level of the room. But the mid-band, to demonstrate a point with this, I can take the core out completely, and that transformer behaves from about 1 kilohertz up, exactly the same as it only needs a mu of 1. Because the problem is, we know that air is a mu of 1, but when you stack a bunch of copper windings together, there is mutual conductance between the copper, which raises the apparent localized mu, because there's a local flux field. So it doesn't quite behave as if it's a pure air core, because it's not a single layer solenoid, which is what your normal air core inductor calculations are based upon. So the core is only doing the work, and the core only progressively comes into function as you go down in frequency. So it doesn't really do much to the frequencies close to that cutoff point. Well, 10 dB at 60 dB down, I can live with that. But if I put about 10 dBs of feedback around that, I can recover that to perfectly level. And I can demonstrate it with a square wave, where the square wave will stay the same shape more or less all the way down. Now, the other refinement I do on this transformer for some of the broadcast applications is I have the second part of that, I have a cathode winding that is part and parcel of this transformer, which is on a 10-to-1, approximately 10-to-1 ratio. So now there's a little bit of cathode feedback, if you like. And I drive that. The gain of that means that I have, in my case, I can make that output approximately 6 dBs more output than the voltage across this cathode. So I can make this have a gain of 6, a gain of 2, by the ratios of the windings. In practice, that is wound. So in this particular case, it's actually a bit more than 10-to-1. I'll call it 16-to-1 and 8-to-1. That's the ratios. The anode then becomes less in how I do the calculation, and as long as that tube has a reasonable amount of gain, but because it's benign, local, the stability of the product isn't a problem. There's a small amount of feedback, but now I've got the lowest levels I ever want flat, and I don't need any more complexity of the drive circuit. So, I mean, the quad amplifiers used a bit of cathode feedback, perfectly acceptable. And word feedback, people talk about your cathode follower. They always say it has 100% feedback. It doesn't. Because feedback, by dictionary definition, means you've got to take something from a port and put it back into another port. On a cathode follower, where is the point of feedback from out externally from which port to which port? There isn't. So it isn't feedback. And you have to configure, when you have your power supply, if your datum pointer, you put your oscillator here, or if you put your oscillator to this point, depends on where you put your oscillator, whether that becomes a cathode follower or a plate follower. So it's all a matter of semantics. So That
Thank you.
it's not a feedback. The reason it will also have, we discussed that yesterday, the reason you'll have parasitic oscillations and things is purely due to the behavior of a tube with finite inductances and finite capacitances in its construction, with external capacitances makes what I would call a Colpitt's oscillator in the first order. And so that's why you're trying to avoid that. And so I'll come to my other point on valves while I'm at it with the PCC88 or ECC88.
Trying to say that this is actually feedback isn't bad.
If we take an ECC88, I'm connected in cascode, and I'm not interested in the GM of the tube. My own practical experiences, if I have an anode in resistance, and this is what is used in the 859 amplifier of 510 kilo ohms, less than a million, and I have 400 volts here to start with. The ECC88 triad configuration, if I have this point as 20 volts here, I can pull comfortably a milliamp. Now the maximum GM of a valve we know is when this cathode voltage here to grid is approximately minus 1.3 volts. So the ideal of trying to operate a tube as near as you can to the starting point of 1.3, beyond minus 1 you have grid current because of the electron cloud given off from the cathode, and that's it, everybody knows about that. Right, so if you can make it 1.3, you can optimize the GM. Now, the point, we all know that the triads look like that. In this cascode, what I've ended up with is a product. Is a family of curves like that, as near a perfect a pentode characteristic as I can possibly achieve. In this particular configuration, I can get a voltage gain of over 400. So for 1 volt in equals 400 there. And it's highly linear. There's steps between all the current parts of the curves. This tube, because it's operating also with a low grid to cathode, all the current coming out of this triode goes into here. Now, a standard triode, as it turns on, it falls back on this curve and needs more and more grid voltage to get it to turn on harder. When that anode, I'm now operating this tube purely on this current part of the curve, because the anode is now held constant and not allowed to move. Therefore, that triode works on this current plane. Therefore, the GM of that tube is incredibly high. And it transfers all the GM energy back through to the top tube to give you a high voltage gain of about 400. EF86 has a gain of about 200 if you sweat, 150 to 200. The 6BA6 pentode, 250. Now, the E810F pentode, RF pentode, the best you can get out of that is about 300 when you optimize. But the ECC88, for the same number of pins, 9 pin, one piece of glass, has a huge amount of gain with high linearity. And on the 859, I merely, with a voltage divider, go into a cathode follower to screen drive the power tube and have this tube running only on 250 to keep that tube in safe operating area. And I have a voltage divider here which gives me DC coupling and DC coupling into the power tube. And I have a capacitor here just to provide high AC coupling. Since the input impedance of that cathode follower is relatively high, its loading effects on that 510 are very benign. The capacitance of the anode to grid is 1 picofarad. So the bandwidth open loop of this amplifier is well in the order of 50 to 100 kilohertz with, flat before I compensate. Then the point was, there's the cathode on the EL509. I merely took that point back to this as my bias and deleted those parts of the equation, so that as the tube tries to turn on too hard, it will lift this tube up a bit. As it lifts this tube up, this tube turns on a bit and pulls that point down again. So it's a self-compensating DC loop. On the screen drive, it's working plus 20 volts relative to the cathode, or plus 40 volts relative to ground. And the screen is driven from 0 to plus about 60, which is not very difficult for that cathode follower. So it's about 20 volts of AC drive needed to drive that tube. Well, out of that 400, that leaves me a gain of 20 left. Well, I can get in reality, it doesn't quite turn out that way, and then I end up with a global feedback of 6 dBs, just to pretty up the last bit of distortion figures. And that's how the 859 came into being. Self-compensating circuit. The current version, I have refined this and taken it on a little bit further, so it will always, regardless of these tubes. And so people, when they replace tube roll on 859s, wonder why they have problems. This tube has to be selected for the bias of the output tube. Some tubes turn on a bit harder and allow this cathode to rise to about 24. Some will end up at 16 volts. So this tube is selected to end up with that. Or, alternatively, you can adjust the cathode resistor slightly to do the simple bias correction. So it has to be class A. That's the 859. And the reason I call it the screen drive, I called it enhanced triad mode, because in the Mosfet condition, a junction FET is normally, like a tube, backed off negatively to turn the Mosfet off, the junction FET off. Or you bring its gate towards 0 to turn it on. Well, a Mosfet, at 0, it's completely off, and you have to go to a voltage something in the order of plus 5 volts before it starts to turn on. And at 7 volts it's on hard. And that is always being called an enhanced mode MOSFET. And consequently that was where I took the word enhanced mode triode. Because nothing much happens until they get to a certain voltage on this power tube, when the grid 1 is tied to cathode effectively. In the practical circuit, grid 1 is taken about minus 1 to 2 volts, because some of the Russian tubes do not turn off properly. They have inherently bad leakage, and they do have some glitches when you try and turn them off with absolutely 0. So I have a tiny amount of back bias to keep the emission cloud between grid 1 and the cathode out of the equation, and then it will behave. And that's the simple answer to that. There's nothing, it's triodes, but it behaves exactly like a pentode, except that they're actually, compared to pentodes, these lines are actually almost a perfect constant current. Now, one of the arguments I'm going to just a brief touch on it was yesterday, everybody was talking about. I draw resistors as squiggles because this is British Standards 1962, the method.
It's also had that drawers in Japan, isn't it?
Now, a constant current, people use some solid state device as a constant current. And they're saying, yes, if you have an input here and you've got your feedback here, for argument's sake, these two will balance accurately because it becomes immune to the tubes. In practice, there's one thing they haven't thought about on this constant current. What about common mode? What happens in common mode? Say that you put plus 5 volts in here, and you put plus 5 volts in here. That grid has taken those cathodes 5 volts up, but the anode with the constant current has stayed at, say, 100 volts. So this valve has got 5 volts less across it. So is this. From the curves on the graph, the voltage difference between that grid and grid will change. So it's no longer got a good common mode. So why have this constant current when that is defeating your object of a constant current? If you did had a second set of triodes down here in cascode on your constant current, and you then had a voltage between that set of triodes and the bias of this tube, and you fed the audio in there and here. And as that tube moves up and down, so it's constant. Now we have now that is a perfect constant current. So when people talk about these constant current sources, wonderful. Now, what is the difference between that on error and the good old-fashioned Blumlein method, where the cathodes, I'll draw them as 2 cathodes, had a very long resistor. If I make that minus 200 volt, and I have 2 milliamps, say 2 milliamps, and that's 100k, to all intents and purposes, that's bloody near a constant current. Why do I need semiconductors in my 1930s amplifier?
Not to have that minus 200.
Well, you make 200. What's difficult in making minus? You have a power supply with a full wave rectifier. There's no difficulty in having another pair, often a pair of rectifiers to generate a negative voltage. If it's that, it'll be high voltage and you can tap it down to about 200 to 300 volts. And then you'll have a nice constant current. If you make that 400 volts minus 400, and that's 200k, it's even better of a constant current.
You could put in a choke as well.
But at 2 milliamps, we're getting, to get real, a choke to be used instead of that, with sufficient inductance, gets very costly. I mean, I can do it as a pure technical exercise. If you want to make a choke bigger than that coffee cup to put inside for your little 12 ECC 83 at the beginning, and you want to do it for every stage, let's get real. And that's the point. It's not a constant current. People haven't seen the wood for the trees. They didn't think about this common mode, what's happening to the anode. So it's not constant current. You can say it's nearly constant current source. And if you take it to a cascode, now you'll have constant current. So that's my take on how I operate triodes. Not conventional. Cascodes, make them like pentodes, but I don't have the partition noise of a pentode. So now I have a perfect pentode. It's really quiet. And I've used that on a microphone amplifier, as a capacitor microphone head, because I can make that input impedance ever so high. So it works beautifully. Now,
If you find a linear, only 20 volts anode on the bottom,
it's very linear at 1 milliamp current. It's incredibly linear. I suggest you try it.
1 milliamp.
Okay. Here's a little teaser for you. This is a microphone amplifier. We'll ignore the fact that there's a transformer. We'll use a resistive load, and it's 100k, which is typical value in a Neumann microphone amplifier, a head amplifier, and that's capacitively coupled to the transformer that goes out to the audio to drive your output. We'll neglect the bias. We have a capacitor microphone here. That's your actual microphone, and we'll ignore the bias. This normally would be returned to a bias to polarize the compact capsule, but for the argument, that is the normal amplification of a capacitor microphone. And this capacitor on a 1-inch capsule, 25mm capsule of a Neumann, is around about 100 pf. So you need the equivalent of about 1 gig ohm to get down to minus 10 to 10 hertz. Time constant of 100 puff over 100 gigohm. So I cascode this and bias, I'll put bias here and call that 20 volts. It's it's half a milliamp on a microphone amplifier typically. It's only 120 volts is a B plus on a typical, because your polarizing voltage is 120 for capsule, or half of 120, 60 volts, sorry. Because for a figure of 8, you have 2 capsules. In a figure of 8 microphone, you have the 2 capsules, and this capsule is coupled by a large value capacitor to this capsule, and this one has, via a resistor, a bias that goes up or down to change the phase of that to make it either a figure of 8 or an omnidirectional or cardioid. Right. This is open loop, but the response isn't very good. People don't even spot there's a trick in Neumann microphones. I have a capacitor from this anode back to this point on the capsule. I'll call that 10 PF. Assuming there's high gain in that triad, what is the gain of that circuit? Anybody can answer me?
Ratio of capacitors.
Because you've now made a capacitance divider. So now I can control the gain of that. That's now 10 times the gain of the grid. The output transformer is 10 to 1. The output is exactly equal to this voltage. But it's a feedback of sorts. It has just about got out of one port back into another. But because it's a simple 6 dB one stage, it never oscillates. It's rock stable. People see this in Neumann's and rip it out, wondering what it's doing. They don't understand its purpose. And wondered why, when their Neumann mics now have a response sort of like that. They think it's why they sound, oh, it sounds charming. And the point is this now linearizes the whole circuit to the capsule, so that the pressure on that capsule from a low frequency to its resonance is a straight line. And that way, it's easy to achieve below 10 hertz response out of a capsule. That's what that little fella is.
What was the tube used?
The Neumanns use AC701s, which is not a cascode. There's a bit less gain. So the perfection isn't quite as good as if you cascode it. But the Neumanns have this sort of value. It varies between 7 and 10 pico. It's adjusted because you've got stray capacitances. So if you make it 7 picofarad, you've got about 3 P in the wiring and so on. It ends up as a nice 10 to 1 gain, dropped by 10 to 1 back to give you 0 gain down with a low impedance drive down the line. Because that capacitor conveniently lowers the output impedance of that. So when that's driving the transformer, it's nice and low. It's a feedback, but it's not a deleterious. I suggest people do some modelling on that.
How does the tube survive the 1 gigaohm grid resistance?
But you have a 1 gigaohm resistor, and if you have that biased low, so that the grid's about minus 2 volts, there's no grid current worth talking about with a good conditioned tube. The AC701 was designed to have very low leakage of grid current because they put the grid at the top cap of the tube, not at the bottom, to keep the path from the other electrodes very long on the external, because glass is a good insulator internally, you're not going to get, and you can get a leakages well into the femtoamps, immeasurable. So your gigohm, it'll space charge and stay at minus 2 perfectly happily. So that's the input impedance of that fella.
But you could do the same with other tubes than the AC701.
Oh yeah, of course you can. But the 701 was made by Telefunken specifically because a single triad with roughly the same characteristics as half of a 12X ECC83, about a mu of 70. But it was a single, very small package, and it had a 4.5 volt filament, so it was easy to and only 100 and something milliamps filament current, so they could run it remotely down the power line, because HT for the polarizing and the filaments, that's 4 wires, plus 1 wire to vary the polarizing voltage on that capsule, this potentiometer switch. It's 5 wires to balanced output 7-wire conductor, 7-pin connector. That's how it all happens. And you want the filament reasonably economic. Now on microphone amplifiers, because of the long length, you could have anything from 10 meters of cable to, in some installations, like when they do the Pink Floyd concert, where you've got the band inside and they've got cables running all the way out to trucks outside, a couple of 100 meters, 300, 400, 500 meters. The power supplies of microphone amplifiers is usually more or less a constant current source for the of DC, starting with about 12 volts for the filament. So it will compensate. Whatever the cable length, the filament in the valve gets the same voltage. And that's how they deal with that problem. And the other currents are so minuscule, it doesn't matter about the thickness of cable. The losses are insignificant. And the lower put impedance from here, on your twisted pair conductor, you can transmit that a long distance. So that's a food for thought point on that.
What you haven't said is the 701 is now worth about $2,000 each.
Yes. And the Chinese were allegedly supposed to have made a 701 copy, but I haven't seen one yet. And JJ was talking about it, and I haven't seen one yet. Nobody's ever bothered. And I was trying to get the Yugoslav factory to make one when I went there about 6 years ago. Because they've got all the parts, the glassware and all that. Not that difficult to make a 701. Telefunken selected them on production. After production, they selected them with the K, meaning selected low noise. And the other ones weren't as quiet. And there was plenty on the market that haven't got the K on. They're a bit splutterier, but they'll get you by. They'll rescue a situation. But 701, the only thing is that the cathode is similar to an ECC88. It has relatively low surface interface capacitance. So in a microphone, you should get 5,000 to 10,000 hours before the flicker noise and all the other noises get in the way. The emission doesn't fall off. It's usually the failure of the tube in a valve in a microphone is predominantly due to flicker noise and splutter noise increasing with time. And that's why they're expensive, because people are wanting to replace them. And don't get me started on the other type of valve in the rarity. So basically, that's what I'm trying to work if I got along. Right. In essence, as I say, I've covered more or less what I wanted to cover, but basically my message was think about...
You had another rule of thumb on an earlier page.
Sorry?
You had another rule of thumb you were going to explain to us on an earlier page.
Let me try and remember. I think I kind of covered that. Sorry. Mu metal core, 5K. Simple answer, 1 square centimetre. 1 square centimetre is roughly 200 turns per volt for a very low frequency, 20 hertz. Just rather than doing the calculation. If you wind a typical mu metal, you get all the... I don't care about the inductance.
Tim, there's a question very important over here.
Yes.
May I please interrupt? Okay, go ahead. Thank you. I had a question according to the graph. I think it was a mu against what? You know, you draw it there.
Sorry.
This one.
You plotted this line here
Yes.
against what? What's that here?
That's flux. This is flux. No, that's 0.5.
Flux.
5 Gauss or 5.
You say it drops off at very low
It
level.
doesn't. That was the flux goes. That's 0 flux. So this is mu. That was mu in this flux.
Okay.
And the mu does not drop off as you reach 0. That's what I was trying to say. And the saturation of permanent is in the board roughly 6K.
I've already rated that to the